Right, we should be live here.
In the green, in the group chat, if you could pass the live link, I'd appreciate it.
Okay. Let me get
when you get round to it.
Yeah, we are now live, George. I'd just like, first of all, I'd just like to introduce the panel here. It's a great pleasure to have George back with me as usual, and along with George, we've got Conspiracy Catz, who's got his police box thing there, who is sort of initiated this discussion, which we're going to be focusing on today, which is this observation of Mount St. Helens and Mount Rainier from Portland in Oregon. And we also have the chap who actually took the photograph, is Isaac. So hello to Isaac. Is that okay to refer to you as Isaac?
Yeah, that's fine.
Great. So we've got, so this is, and we were going to be joined by Phillip, Phil, the physics guy as well, who is who I've been working on the last God knows how many, 6 months or more, on a big presentation about Isle of Man observations and detailing refraction and ray tracing, and he's been able to do a ray tracing image for me, which I'll be showing you. So let me just do some housework for let me just get the link for George, and then because yes, I should be looking at that as well. Sorry, just give me a second. Oh, bloody thing. Right. Yes. Right. Right, there's the link to the watch page for people. Right, okay, well, I'm going to do a little presentation first on my analysis, and then anybody can comment obviously at any stage, but I've got a little bit, sort of several stages to go run through what's been happened in the past and my analysis of it, and then yeah, but you know, chip in whenever you like, and then George may perhaps contribute on the refraction case, because we're going to be talking about refraction as well, and some of the claims that have been associated with response. Anthony Riley was trying to make some claims about refraction, because in trying to invalidate Conspiracy Catz's video, he made a number of mistakes. He got all his maths all wrong, of course, as he does with everything, and but not only in the way that Conspiracy Catz was trying to induce him to make mistakes. He made some additional ones which he didn't allow for the observer height in his angular size calculation. So he managed to get everything, just about everything wrong you could, except the basic numbers. So I'm going to be going through how you do this calculation correctly. And then we're going to talk a little about refraction, because Anthony has now decided from SLI, he's now discovered apparently that light refracts upwards, and we're going to be talking about that as well. And George is going to be able to tell us some practical experimentation he's done, or observations he's done on refraction and way that light, the density variation with height. And then we'll be able to say, well, that's a very silly thing to say, Anthony. And he's picked up this from, I think, someone who made some a PhD chappie who's of a rather odd chap who seems to believe in the flat Earth. He made some observations from Worthing to Brighton in the UK about a week ago. Right. Yeah, Conspiracy Catz, that link is just if you want to see what the chat is going on, if you want to comment on, see the chat on the video. So if people will be asking questions. So really, it'd be nice actually if someone was observing that. I should be doing that myself, but while I'm making, so if anyone wants to observe the chat and then relay to me any questions in my presentation, that would be very useful for me, because I'll be obviously in the middle of my presentation. And yeah, so, great, thanks, Catz. That'd be really, really useful, because who knows what I might be doing something stupid, or I might be not understanding something. So right, so I'm going to start off my presentation, and then dealing basically, obviously the core thing is Isaac's photo, and I'll be going through that, and he can obviously correct me. Right, so my presentation.
Hey, Rumpus, before you get going, that link you posted me is the SLI hangout, not the live one.
Oh, bloody hell, sorry.
It's not. I've got the live one on my phone, so I can see that.
Oh, right. Did I really post the wrong one? That was very stupid of me. Sorry, that's.
See if I can do it.
Right, sorry, George. That's absolutely stupid of me. Okay. Sorry, George. That was absolutely stupid in the extreme.
While you're just doing that, Rumpus, I just want to give a big shout out to Isaac for. I mean, he took the photograph. He was inspired, I think, by you know, the Miles Davis photograph, but realized he had something just as good. And you know, the whole sort of collection of data, the collection of numbers, he's worked really hard on this. So you know, Isaac, just I think this is your moment to take some glory for taking down the flat Earth debate team. Well done, mate.
Hey man, I appreciate it, but you know, it was all you. If you wouldn't have helped out and pushed it, it would have went nowhere. So I thank you, man.
Right, so hopefully you can see this thing what I'm doing here. Right, this I must admit I'm a bit rushed, so I haven't actually got this is the well, I was going to go through the photographic evidence, then some of the locations, how we see things, refraction, modeling on a flat Earth, modeling on a spherical Earth, and the errors in the modeling by the flat Earthers. So here's Isaac's marvelous photo. It's very nearly horizontal. Lovely picture. And so I don't know whether you do this, Isaac, to actually, because you saw something, or you just had to be taking some pictures and then spotted that something was aligned?
No, I actually like Conspiracy Catz said, I'd seen the Miles Davis photo, and this park where I took this just is like less than 5 minutes from my house. So one day, me and my wife, we just went up there and you know, took our cameras and we just took a whole bunch of pictures. But yeah, I had a little tiny tripod. I just put it down and I took a whole bunch of pictures. And there's actually, I don't know if you guys have noticed the park, but you can also, from that same location, you can see Mount Adams and Mount Hood. So it's really just an amazing spot. It's basically a tourist
right
spot.
Yes, right, okay. Yes, so yes, I can imagine it's got a great view there, and I'm back to show, in fact, I think you've done it as well, because you've been quite thorough about this, Isaac, and that's reassuring me, because you took lots of good photographs and you went to Google Earth and Peak Finder and things.
Well, when I was taking it, I was trying to think of every little thing that they were gonna say.
Right,
the
right.
viewer height, you know, the location,
Yeah.
you know, just everything I possibly. So I tried my best to, you know, to get it, but really the thing is, it's just anybody could go there at any time on a clear day and do this.
Yeah, I mean, it looks as though you've taken some care here. So, right, so here's an annotations on my anybody who's seen Isaac's channel. I should really put a link to it. Yeah, I should put a link to that actually in the in my thing to Isaac's, because he's got his analysis. I haven't used his annotation here, but here's the basic point. Here we have Mount St. Helens. Here's the we have Mount St. Helens at a distance of, which I've forgotten. I think I missed out there. And here we have in the further distance Mount Rainier, and here we have the horizontal for the observer, which I'll be showing you how that's obtained in a second. And I think Isaac did it in the same way by using Peak Finder. And here's the key thing. This is the alignment here. This is actually the crescent ridge on St. Helens, and of course Conspiracy Catz got Anthony Riley to just sort of randomly not pick the right thing out when it caught him. Absolutely, he wasn't paying attention in his analysis when Anthony Riley decided to use the value of the peak of Mount St. Helens rather than this ridge. Although Conspiracy Catz did point out, he did do it in a rather sort of subtle way, which obviously meant that Anthony didn't spot that's what he was referring to. And of course, he went off on his little charge trying to do things on the peak of the mountain rather than, in fact, what Conspiracy Catz was pointing out, which is this little ridge here, which aligns with Mount Rainier in the distance. So this is at 86 kilometers away, this ridge, and this mountain here is at 167 kilometers away. And as you can see in the picture, and Isaac was at 323 meters, which is 1,075 feet odd. So I think I'm going to work everything in meters, I'm afraid, here, guys, if you're American. So that's the key thing that Isaac spotted, is that he saw these two things huge distance away. I mean, let's remember this. So there's a difference there. This is twice as far away as this, and this is 86 kilometers away. There's 167 kilometers away, this thing over here, and they're just nicely aligned, and so that would be a great test. So it's a great test. There's obviously really clear sky to be able to see that far. And so obviously if these two things align, well, that we should be able to use that just as Miles Davis did, to say, well, if these things are aligning, then we know the heights of them, and therefore we should be able to say, well, on a flat Earth, whether that should be occurring, or whether or not on a spherical Earth it should be occurring. So it's a great test to determine, from our knowledge of the way the Earth's drops and things, whether they should be aligning. It's a great test. If those things aren't aligned, if one model, the flat Earth model, has them aligning or not aligning, or if the spherical Earth model has them aligning, not aligning, one of those models is correct. So you put in the model, see what the model predicts, compare it against the reality that Isaac's got here, and then you see, well, okay, so which model is correct? And if we look here at Peak Finder, this for an observer 320 meters. Again, this showing this is where the horizontal came from. This is the thing, and if you overlay them, you can see here that the Peak Finder overlay on the image that Isaac took is exact. Well, it's not quite exact, because one thing that Peak Finder doesn't do is allow for refraction, but the refraction isn't a really huge issue for this, but it does affect it a little bit, and it actually lines up with this feature here and those features there. And you can also see you probably can't actually. I'll change the transparency on this so you can see how well. Oh bloody hell! Wrong thing. Hold on, sorry about that. You can see here if I change the transparency on this. There's the image, and I can bring in the overlay of the Peak Finder, and you can just see there's a slight discrepancy. So I don't think Isaac quite got it horizontal, but goddamn close. So he did a good job there. And so you can see that for a start, we've got something that is based on the globe matching the reality for a start. And you can see here that yes, I should have mentioned this is the Mount Rainier, and it's incredibly close. So for a start, we've got something that relies on a spherical model of the Earth, giving us these the Peak Finder giving us these image, and we've got that overlaid with the real image, and it's exact. So that, really, from there you could just stop now, but no, we're going to carry on and do a bit more. This is what it looks like in Google Earth. This is not taken from quite the right thing, so that actually it's quite close actually. So you can see their line in Google Earth as well. This is I've magnified. If you know what you're doing in the Google Earth, you can actually magnify the images. And so even though this is 86 kilometers away, if you know what you're doing in Google Earth, you can actually zoom into it and get a similar effect you can in Peak Finder. And so you can see there again, those the crescent ridge, as it's called. And this is identifying this is looking down in Google Earth at the crescent ridge, as this is called. And it's at 1,979 meters. That's the location apparently Anthony Riley couldn't find, even though it was quite obvious. And I think Sly showed it to him as well inside the hangout yesterday, but apparently Anthony couldn't find that there. And this is the crescent ridge on the in that contour map here. This is the ridge itself. This is Mount St. Helens. There's the ridge and the actual spot that is along here, and it's actually a water valley, little river down here actually, and so that's the actual ridge along here. It's called Crescent Ridge, and here is the Isaac's location. He's in Portland, I think it is, Isaac, down there.
Yep,
right.
Portland.
And he's looking along, and here we can see this 100 Mount Rainier, Mount St. Helens. There's the line of sight of the two nicely in line. So it's very incredibly convenient. You've got two very significant peaks that obviously you need to be really tall, obviously, to be able to see them 167 meters, 167 kilometers. So the fact that we've got two peaks actually in line and right next to Isaac, he's very fortunate there. That's a fantastic long range. I mean, this is going across states. I mean, 167. I mean, we're measuring the curvature of the Earth across 167 kilometers here. It's just an amazing alignment here of something. To be able to do that, so he's very fortunate there to do that. And obviously, in fact, there aren't any other convenient. Yeah, in fact, there aren't any other really convenient alignments, are there? These peaks to somewhere and observe in the distance. Yeah, that's. And of course, you had to have get quite a decent height to get to see over all the crap and things to get a decent look. So you're very fortunate to have a nice 323 meter thing. So when we say things, so there we have the image, but we need to work out how we actually see things. So. We have all these sizes and things of objects, but what a camera actually does is it performs a perspective transformation on 3D images, and so you need to understand how that works. This is something, of course, that flat earthers don't understand. They don't understand what perspective is, and they certainly don't know the formulas for it, which are not difficult, but they don't even understand the concepts. And they don't understand. They do vaguely understand. They seem to have caught on now to the fact that what you see in your eye or a camera sees is actually an angle. So if we imagine here, I've got a point, an object at 3 different distances. They're twice each. So this one's twice that, and this one's twice that. And we move the object closer. Then the way the eye or a camera sees it, it of course can't see distances. All the camera gets is it gets a light ray, and the only thing it can register is the angle. I hope this is clear enough. The angle of the ray that comes in. That's the only thing it registers. So when you're looking at a picture like Isaac took up here, every single one of the pixels on there is effectively an angular coordinate. I didn't have time, unfortunately, to put an angular grid on here showing you. So each pixel on here is effectively at an angle. So I could have put, you know, a bearing would be going up to left and right, and then up and down would be an elevation angle, or what do they call it, declination. So each pixel is effectively an angle. The way I'm not going to, the eye and camera see slightly differently, but I'm not going to talk about that. The eye actually uses pure angles because it's not a flat, but cameras actually have a flat viewing plane in them, which means they don't quite have, it's not quite just an angle, but I'm not going to go into that. I did have a huge diagram I drew all about this inside. It wasn't really worth doing. So you can just think about every part of a picture is just an angle, and it could be long, it could be close, it could be far away. And as you can see here, as I move the same image, it's got the same height. All that happens is the angle of it changes, and obviously its angular size will change, but we're just worrying about its position here. So this is effectively the perspective transformation. As things move, you know, come closer, the angle that they subtend to the eye or a camera increases. And right, so what we're doing here to work out, to do the maths, to determine on a flat Earth whether or not these things should align, what we need to do in this ridge here, if we want to know what angle this should be, what angle this should be, because as I say, vision and pictures, cameras all work on angles of the light. So we want to know if the angle of this crescent ridge as it subtends to your eye is the same as the angle of this mountain subtending, Mount Rainier subtending to your eye. If those two are the same on the spherical Earth model, then we know that there's a spherical Earth model. If they're not enough, and if we work on a flat Earth model, the angle is the same on a flat Earth model, then we can say then that model is correct. So first of all, we need to work out how to get those angles, and so we've already established all about angles. And what you can do is a very simple way, and I think Conspiracy Catz covered this in one recent video. You don't all this angular size stuff and angular position. When the angles are very small, there's actually an approximation you can do, particularly if you work in radians. This is one of the reasons, part of my other presentation, I've got about radians, and this is actually part of a circle I've got here. And when the theta, the size of the circle, becomes very small, you can actually ignore all the tans and stuff like that. And the actual approximation of the height of something is simply, you can imagine that as this angle gets very, very small, you can see here, here's a building or an object you're looking at. And as this angle gets smaller and smaller, this S, which is the length of the arc of the circle, becomes so small, it becomes straight, it becomes horizontal, it becomes vertical in this case. And therefore you can say that a portion of a circle is the same as the height of an object. And there's a very simple formula then, because the length of a part of an arc of a circle has a very simple relationship to the angle in radians and the radius, and that relationship is simply here. As the angle gets very small, the height of the object h here is simply equal to the distance to the object times the angle in radians. So that very simple relationship. It's a small angle. It's very accurate for small angles. So although I've put an approximate sign there, it is actually very accurate. And we're there. So d is the distance of the object, h is the dimension of the object, the height, and theta is the angle size. So those are two relations. You can sort. These are just two things swapped around. So the angular size of an object here, theta, is simply equal to the height of the object perpendicular to your line of sight, divided by the distance. So that's the angular size in radians. If you want to convert it into degrees, as something that Conspiracy Catz did recently, you need a scaling factor to do that of 180 over pi. So if you want to know the angular size of an object, rather than doing, you may Anthony Riley and others go to the angle size converter on websites and things, you could do it yourself just simply by implementing this formula. Get the height of the object just divided by distance of the object times 180 over pi. This is for small angles, so don't start putting, if you're standing right next to something that's occupying about 70 degrees of your side, this isn't going to work. But this is what for all this zoomed in stuff, this will work. Right, so now we know how to get the angular size of something. We've got a simple formula for it. So now we know that the eyesight works on angles. We now know how to work out the angular size of something. So now we can go ahead and say, right, we've got a flat Earth model. What is the angle of something? And then see if the angles of those 2 points are the same on a flat Earth. Well, okay, so here's our flat Earth. Now this is to scale in the horizontal direction and in the vertical direction, but the scales are not the same in each in the two dimensions. So for instance, the this is the correct distance here to scale of this is the ridge here, Crescent Ridge, just there where this arrow is, and there's Mount Rainier, the position we're interested in, and it is in fact that, as you can see, almost twice as far away as St. Helens Ridge. And similarly vertically, these are to scale, and this is Isaac on his 323 meter position. This is him bending down taking his photo, and so there's a gap between him and the flat Earth of 323 meters. This is the thing that Anthony Rye didn't take into account when he did his calculations of angular size. He just pumped in the sizes, and so of course it meant all his stuff was off, because of course we're interested in the angle above the observer's horizontal. So we have to subtract the observer's horizontal. So to get the angle of this thing here, we just simply need to subtract the 323 meters from the height, and that means we end up with the value of 165. That's 1,656 meters. Its original height is 1,979 meters. So the angle above the observer is 1,656 meters. The distance to it is 86 kilometers, 743 meters. And if you do the calcs, you'll see that gives you an angle of 1.09 degrees. So the angular size above the observer for Crescent Ridge is 1.09 degrees. If you do the same thing for Mount Rainier, again, take away the observer height, it's got an original height of 4,392 meters. Take away the 323, you end up with 4,069 meters above the observer. So you end up with this triangle, and you then end up with the angle of 1.39 degrees. And so you can see, for a start, here we have these angles are not the same. To be this, as you can see, the angle that's coming into the observer, these two lines are different angles, 1.09, 1.39. So we've got two different angles to the observer. How different are they? Well, I've put all the information in these boxes if you want to go and check. So I'm going to publish this as a website as well for people who want to follow this. They don't have to go through all this video. They just want to read through and go to the favorite bit. I'm actually going to publish this as a website, so you can peruse at your leisure. And so we see here we've got 1.09 degrees for Mount St. Helens and 1.39 for Mount Rainier. So there's a percentage difference there of 27%, which is a lot. So in other words, in here on this image, we would expect the difference between these two, the ridge and the mountain, to be 27% different. Whatever the number of pixels, I meant to measure this actually in pixels so you could actually do this, but whatever the number of pixels is to this ridge, this one should be 27% higher. That's what that 27% means. And as you can see, it isn't, of course. The ridges are exactly, just about within the same. So, okay, so that means that the flat Earth model, and we haven't allowed for refraction here in this. Now, you could say, oh, hold on, why haven't you done that? Well, when you on a flat Earth model, refraction actually doesn't do very much. Because I won't go into great detail, but on refraction, it actually is much greater on a rounded Earth because the angle of the light hits the layers at different angles as it progresses. And I might detail that if people are interested later on in this. I've got another presentation I can do on this. So I haven't allowed for a refraction here, but it turns out on a flat Earth, refraction has a much more minor effect than it does on a spherical Earth. So I'm justified in doing that. So we've got a 27% difference in our what our model predicts and what reality says is there. So obviously, we can reject that model. And wonderfully, this is the thing that Phillip, who's not here, was hoping. This is actually some of the ray tracing that will be appearing in the thing I've been working on for over 6 months with him. And this is an example of his work. It's just absolutely fan-bloody-tastic. This is a view using a ray tracer and allowing for refraction. From the observer point that I see, because I haven't had time to annotate this, unfortunately. And you can see here, this is what would actually happen on a flat Earth. This is ray traced, allowing for refraction, allowing for all the conditions, etc. It's just unbelievably brilliant, and that's why my presentation on this 6-month thing we're doing is can be absolutely brilliant as well. We've also textured it to indicate distance, and also height is dependent on the color. So things that turn the distance are a different color to the things and low down. Anyway, but the point is, you can see that Mount Rainier there is actually at the same height as St. Helens, using a ray tracer with refraction. So fantastic stuff there, and we don't see that. And as you can see, that's not what we see in the picture that Isaac took. That is not the same as that. And so the flat Earth model, again, so then the confirmation here, by actually doing a full-blown ray trace of Isaac's observation, so we can reject that. So let's do a modeling on the spherical Earth. Now, obviously, with the spherical Earth, you have a much more complicated situation trying to work out the distances. So I was up here just able to use the height of the mountains above the flat Earth to get the angles. But of course, we've now got to allow for the curvature of the Earth. And so we've got to work out these lines of sight, what's hidden, where is the horizontal for the observer. So here, for instance, is the horizontal of the observer here, but there's also quite a lot obscured from the observer. So you can't do what Anthony did, which was just use the angular height, angular size, because there's a great load missing that's below, and it's also shifted below the horizontal. There's a different amount that's shifted. So if you do, I'm not going to go into the maths of all this now, but if you this is the equation. So if you have if you have a building in the distance, the amount that you're missing off the base off the building is this value h, the hidden value, which is what the value you'll be filling with in the mixed west Earth curve calculator, the hidden value. And this, he uses a rather simplified form of the equation, but it's actually, his is quite accurate for the distance that he tends to use. This is actually the full-blown equation for that value of the hidden, what you're losing. And if you allow for refraction as well, this is so the S there, R is the modified radius of the Earth, because when you do refraction, it actually works out, the scaling factors mean that all you need to do is actually to change and multiply the radius of the Earth by a scaling factor of 7/6 using standard refraction. And indeed, it seems that Isaac's conditions conform to standard refraction. So the R there is the 7/6 version of the radius. S here is this distance. The distance to the object is on an arc here is given by S. So here's the observer with the eye. Here's the whichever mountain we want to pick on. S is that distance. So the formula here gives you, so there's S is the distance of the formula, and A there is the altitude of the observer. So you've only got three variables. You've got, well, R, which you can vary depending on the refraction conditions, the radius of the Earth, but the only two you really need to measure out are your distance to the object and your altitude. So that's the formula for the hidden. And then if you actually want to, but of course what we're worried about is the visible portion of the mountain above the horizontal for the observer. That's what we're interested in, because of course it can go below and above. So if you want to know what the actual amount of the mountain is above the horizontal, well, you need to work out what the visible height is. In other words, how big. So here we have the hidden value of this thing. We want to know how big this value is, the height that's not hidden. So if we then shove that in, that's just simply the difference between the actual height of the object and the visible height. And then we then want to know what the angular size is of that. Having determined how much of this thing that we can actually see, we then want to know the angular size of it. And if you pump those values into this calculation here, you end up with a, so if you, using the formula I showed you above about how you work out the, this formula up here, I showed you how you work out the angular size of something, this one. And if you pump up those values into that, so here's the formula. So if you, yeah, so the visible portion is the visible minus the hidden. So that gives you the visible height. Then this gives you the angular size of the visible height. And so if the full formula, and I say V there is equal to T minus H, and H is given by this. So if you substitute all the things, this is the final formula you end up with to give you the angular size on a spherical Earth of an object, including standard refraction. So that's the full formula. And here, if you pump in the number, R is the 7/6 value of the R. We know that Isaac was at 323 meters. So we've now got those two are fixed for both the observations. We're fixing the radius of the Earth and fixing Isaac's position. And so now we just need to put in this formula for the two situations where the distance to Mount St. Helens was 86 kilometers and the height of the ridge was 1,979. But of course that then subtracts the visible height, and you also have to allow for the observer height, which I have done actually. Well, I haven't put that in here, but in my spreadsheet I have. So yes, actually, I haven't allowed for the observer height subtraction. But so yes, actually, this is I only just did this a quarter of an hour ago. So in my spreadsheet, I've now made the analysis, but I haven't done here. So that's a bit naughty of me. But the calculations come from my spreadsheet. So you end up with the angular size of Mount Rainier as being 0.74 degrees, and the angular size of Mount St. Helens is 0.759, and that gives a difference of only 0.7%. So that means that those two peaks should be within 1% of the pixels in an image of one another. So our prediction with the spherical Earth model is that these 2 points, and don't forget that ridge is actually curving. If you remember from the contour graph, it is actually slightly dipping, but it's saying that with it, those two should be within 1% of one another. And of course, that's within 1%, seems to me. And so we can say that our spherical Earth model is predicting there's a 1% difference, and indeed that's what matches the photograph. And kindly, Phillip has also done a modeling of the spherical Earth model as well, with standard refraction, ray traced, for Isaac's position. And as you can see, I haven't actually done this, but if we just put a little line in here, you can see this, the ridge is, because the ridge is actually sloping, but that's within 1% of the difference from the horizontal. So we can conclude that that the model that matches what we see is a spherical Earth, and we can dismiss the flat Earth model. We not only can dismiss the flat Earth, but we can actually confirm, and using this very sophisticated ray trace modeling of it as well, that it absolutely matches the model. So we present a model, it predicts what we should see. This is what the prediction, the spherical Earth model predicts. We compare that against reality. It matches reality perfectly. The flat Earth model makes predictions about what you should see. That doesn't match reality. So obviously you pick the spherical Earth model. And recently in Anthony Riley's been talking about refraction going up. He's discovered this from his other friend, and that's because he doesn't understand. So I might actually show something else, why refraction goes down, and people may have seen this before. Oh, this is actually a picture just while I'm here, in case Sly watches this. Here are lots of inferior mirages, Sly. Right. I'm trying to show the atmosphere. Where has it gone? Jesus Christ. Right. Yes, so here, for instance, is what the atmosphere does. This is a plot of the density, pressure, and temperature of the standard atmosphere versus height. So we've got height in the vertical axis, and we have the situation with 1, 1 on the right-hand side. In other words, at ground level, we set everything to 1. And so you can see that as the height increases, the temperature decreases, and the pressure and density decrease. And that means that the density is greatest at the bottom. Now, that necessarily means that with the greater density, and I can show you this, and in fact, Conspiracy Catz has shown this very same image, and this is the actual logo of my little demo here. In fact, this you may have noticed. This is my goddamn. Where is that stuff on refraction? Where's that bloody tank gone? Oh, there we go. No, sod it. Oh, where's it gone? And here's a fantastic picture by George demonstrating refraction action with a laser beam, showing how it dips down. Yeah, I'm trying to find this bloody. Oh, here we go. Right. So this is a tank, as Conspiracy Catz has demonstrated, where you have actually a tank of water with a sugar solution in it, which increases in density. And so the denser medium is at the bottom, less dense medium at the top. And here's a laser beam coming in from the right-hand side. And as you can see, it bends down. It bends towards the denser medium. And which we can talk about the refraction and things and why that should occur. But this means that if you are an observer here at some point along the light ray, you as an observer or the camera or whatever assumes light travels in straight lines, you will assume that the perceived object is a straight line from your position. But actually the object is below that point because the light has been bent down. It was going up, as you can see, the light was going up from here, but it's bent down. You perceive that as being in this position, you would have perceived this lighthouse as being horizontal to you, but in fact, it's actually below. So it's actually lifted the object up. And of course, Anthony in his thing was claiming that objects are pulled down by refraction because he's got all his things wrong. But this medium here demonstrates what happens when you have a denser medium near the bottom of the tank, less dense at the top of the tank. You will get it arc, the light will bend towards the denser medium, and that means that objects will be lifted up, not down. So this is a model of the atmosphere. Now, obviously, you get these inversion effects which cause inferior mirages very close to the surface of the water, but in this case, with the picture of Isaac, he's well above those areas. You do not need to worry about inferior mirages because he's at 323 meters. You're above, and you're not looking through inversion layers. You can actually just use standard refraction, and so you don't need to worry about these little fiddly things, inferior mirages, God knows what. So, because we know that the air is denser from the graph I showed you, and we've shown from the tank what happens, that it bends towards the medium, we know that things are lifted up, and we therefore know we've got the correct model. And what's more, the ray tracing, that the figures that I put in agree with what we see, and Philip's ray tracing thing agrees, which relies on this very same thing. Where's his ray? Has he gone? Yeah, this thing that he has got in there, the modeling of the Earth using the denser medium at the bottom, and it refracts down, and it matches exactly what we see. So everything comes together beautifully. All the physics supports what we see. The modeling of a spherical Earth supports what we see and invalidates the flat Earth, and the flat Earth model suggests things we should see which we don't, and therefore is obviously invalid. We already knew that, but it's nice to confirm it with a bit of science. That's it.
Yeah, but perspective.
Oh God, solid. Oh no, you've mentioned. Oh damn, I'll have to rewrite this all again now. Philip, where are you? He didn't include perspective in the ray tracing.
Yeah, yeah, it's the only word you need, isn't it? The only word you
that's
need.
right. That's the only argument. You just don't need to think. Don't need to engage the brain. You can just press a button that says perspective, and that's all you need to do as your counter argument. Yeah.
Yeah, I love it. Fantastic. Oh, cheers, Rumpus. That were pretty nailed on. That.
Oh, I'm glad you liked it.
That was very well done. That was so interesting.
Oh, I'm glad I'm glad I introduced you, Isaac. And of course we've got George here, of course, who had some internet problem, but he was going to provide me with his own information on the thing I was showing you about the to support the atmosphere. God damn, where has it gone? Thing. Oh Jesus Christ, I've lost track of it. If I had my web page, I could just click on the link, but I can't. Yeah. Anyway, George was going to provide the some actual practical, because the guy I think that Anthony's now latched onto to claim that, oh no, it could all be on a flat Earth and everything refracts up. And actually, Philip did some calculations on this, and he said that to get the same effect for the ray tracer, to get this effect, you would actually have to have a temperature of absolute zero at the height of the mountain. You'd have to have an inversion layer that went up to, have to get up to the absolute zero to get the same effect on the flat Earth. And that's the line that Anthony is now taking. He's saying, oh, everything refracts up because this idiot who's a spectroscopy PhD guy, I believe that's where he got his information from, who just had a handheld thermometer, whereas in comparison we've got George here who actually built a thermistor rack of up to 12 feet or something with very accurate things that could measure things within, was it 0.1 degree, George, was it your thing? Was he's gone to sleep? Okay, his internet's gone down. I think he's run away. And he built a series of thermistor sticks which measured, I think it was better than 0.1. I think if you did it properly, I think it was less than 0.1 degrees. And so he was able to, and he was in his observations and his experiment, or his observation of where he stuck up all these poles out to 6 miles away on the Rainy Lake in Minnesota. He then showed that was a flat Earth, and he had demonstrated the various refraction conditions and noted all the temperature gradients across this 6 miles and vertically up to 10 meters. And of course, when you get hot things, of course, you get where have I got here? These. Bloody hell, just too much of this here. Oh geez, there we go. So you obviously get things like this, but this is only because you're looking. This is looking at a distance, across something that's got an inversion layer where you've got the air actually is less dense at the surface. So here you are getting light that's actually refracted up, but it only occurs in a very narrow band. It only happens to about 10, about 5-10 meters high. And so this sort of picture here is taken through a zoom lens, something in miles in distance, because therefore your angle to the object is very, very low, and it goes through the inversion layer. Now Isaac's images do not suffer from that, because as I said before, he's at 323 meters, and he's looking well above this hair, because you only get this effect where the ground is heated. And then you get a sort of, and that heats up the air, which makes it less dense, which means that it doesn't follow the graph that I showed you earlier, where the very end, the very bit where mixed on sunny days and on windy days where you get mixing, this doesn't happen. So to get this sort of effect, you need a still day, hot, preferably with a cold. Ranty did this as well. Some of his pictures, in fact, this presentation I'm doing is actually going on about some of the observations that Anthony and Ranty have made. And there, if you do get peculiar conditions, like, for instance, in winter, if you have for instance, in fact, we actually have them at the moment. We've got warm air going over a cold sea. Now that creates the opposite effect. This is causes something which I call superluming, which I will go into detail in this other presentation. But this situation here is where that means you have extra cold. There's a bit the surface in superluminous conditions. We have very cold water and warmer air. This is what believed to be the Titanic situation that caused them some problems. And so here, but in this situation where you get mirages, and also you get compression in the other situation I just described, where the things lower down compress a lot. Ranty hasn't discovered yet you don't get compression along with inferior mirage. You either get one or the other. Yeah, he sees both, and then he keeps on trying to combine them. He keeps on, I get this compression effect. One moment he'll be talking about compression on something, and then he'll be talking about inferior mirages and the same thing. But in fact, you never get them together, because one relies on having an inverted temperature, an inverted density gradient, and the other one relies on a gradient that's extreme the other way. So, Riley's argument against Conspiracy Catz and Isaac's observations and angle, which he started on yesterday with Sly, is that you have an inversion, light refracts up, but this only happens in these sorts of situations when you're looking close to the horizon, an object in the distance over, and where you have a very hot ground level, and then it transmits heat to the end very close to it, which means obviously it then becomes hotter, becomes less dense, less refractive, and therefore you get an inversion. You get refractive inversion. Yeah. Okay. I mean, I've been talking. Yeah. So if anybody else, I don't know, completely monopolize this. The idea was to. Yeah. So it's a great observation, and I think anybody else who's got gets two objects that are in line, but a long way away from one another, then they will always prove the spherical Earth. And this is to get this distance, I think, is quite incredible. I can't remember what Miles Davis was, but this, I don't think it was this long, was it? This is 163 kilometers, and his was, yeah, quite a bit less than that. So this is a really good test over a long distance that the spherical Earth model works, and that the flat Earth one doesn't. But hopefully I've just preempted any attempt. Come on.
No, Isaac, you've got loads and loads of pictures of. I'm like you've got pictures from all sorts of angles of these, haven't you?
Yeah, on the Slack, I took a few different pictures because I knew the whole perspective thing was gonna, be the first rebuttal. So I was trying to get different perspective. Really quick, did you get Crescent Ridge off that PDF I put into the
No, I
Slack?
didn't actually. I got it off.
Oh, okay.
I got it. I can actually show. I think I've even got. Let me show the web page.
Okay, no, that's cool because I finally found it too, and it was off the U.S. Geological Society topographical map.
Yes, that's where I got it from.
I honestly I didn't know it didn't say anywhere, but that's what it actually is called. So
yeah. Yes, actually, you can see here. It is actually a crescent, isn't it? Actually, I don't know where it's crescent this way, and yeah, I presume that's where it presumably gets its name from. This crescent, and this is actually a river down here. I've got. I can show you.
Yeah, it was hard to imagine that they couldn't figure that out, or they needed us to verify it, because I mean it was so simple, but it could be verified. I mean, obviously this is a volcano. This thing has been studied and it measured like forever. It wasn't very hard, but that was really just I couldn't believe that they were, or it wasn't Riley. Yeah, Riley. Wanting Conspiracy Catz to verify the.
Yes,
the
I got. There's because no, actually, I think I got it off the. There's a special Mount St. Helens place, isn't there? Damn it!
A website, you mean?
Yes, there's a special.
Oh.
Was it? Damn it! Oh, here we go. Right, I think this is the one that I. Here we go. Let me. Yeah, here we go. Let me share a different screen here for you.
If you can show your Slack.
Can you see this?
Oh yeah. Okay. That's top of zone. That's where the first PDFs in the Slack channel were from. That right, I added another one earlier today. Yeah. Cool. Yep. Exactly. Crescent Ridge.
And there's a little river, and if you actually look, you can see that actually that is a little gully there that's been presumably been carved out by that water. And there's Crescent Ridge, and the location we are talking about is just there.
Yeah.
I think.
Yeah.
As I had in my other.
Yeah, and it was basically, I had the rough, number, and when I just went to Google Maps to try and put a pin down, it just came up at 6,505. But if you think about it, every height is within that side peak to the top peak. So it doesn't matter where you measured it from. They just happen to be equal right there. And that was the reason why I picked.
Yeah, I mean that's where I found it was just that's where I'm on location. Yeah, and sort of lava plug or something here. It's quite an amazing structure.
Yeah, and the other reason, if I would have known it was Crescent Peak, I would have named it that. But if you look on some of the other maps, they actually indicate where they call it the false peak, where the original mountain was before it blew. And then there's the new peak.
Right.
And I was thinking, I'm gonna get, people are gonna be confused. So I just kind of put in quotation marks side peak. I didn't think it would be, I honestly didn't expect so many people, especially Riley, to not understand that. But it was purely just, it was actually, I was trying to make it more easy to understand.
Right. Catz, has anybody been asking questions in the side chat that I haven't been looking at?
No, not that I can spot a lot of decent conversation, but
okay.
No, although now is a chance if you've got one to whack it on. But let's just have a look. No, I mean, okay, makes a good point. Just saying, whatever we say, they're just going to put it down to presupposition and perspective. They're going to ignore it anyway.
Yeah, but the point is, we have models that produce images like the ray trace one and my calculations, and they match exactly what we see in real life. Our model makes predictions, and it matches real life, and that's the test of the model.
Absolutely, and that's it, isn't it? That's what makes the conversation with them so frustrating. That that not only does it match what we see, but it allows us to make predictions. The whole thing fits together beautifully, doesn't it? You know, and they can't provide one model for one aspect of
That's right,
Earth that works. You know, they
Yeah,
can't.
I mean, yeah, that's right. I mean, all these independent ways of doing things, like the calculations that I did, Philip's modeling of the ray tracing, and the pictures all agree. Everything always agrees intimately. Now, okay, you can get confused by refraction, and as I say, Anthony did some observations of the Isle of Man under some strange conditions, which caused some of the when he went very down, low down, and then he was in some strange conditions, superluminous conditions, where you can get some effects which you then have to allow for. And in Ray Tracer, we have been able to do that by knowing and actually basing on the temperature, because was when Anthony made his observation, we were able to get the temperature conditions for that point. We found out that indeed you had a cold sea and warm air, which means you get this exaggerated looming, the looming I just described with the with that lighthouse thing, wherever it was. If the density gradient is greater, where the bloody hell is greater, you get more. Where did I? Oh yeah, this is the other bit. This is the other bit actually about the why we get refracted. As I was showing, if you also want to think about it, how the atmosphere is like the thing I described up here with the so this thing here. If this gradient is greater, then you're going to get more looming. So just like this has an increased refractive gradient, the denser sugar solutions at the bottom, less dense at the top, therefore more refractive at the bottom. And similarly with the atmosphere, if you just simple way of thinking about it, if you had the atmosphere just being one solid piece of glass, for instance, you would get this behavior here, where I won't go on. It refracts away from the normal when you go from a dense medium to a less dense medium. And if you then think, okay, if you put in lots of, you then decide the atmosphere would make it 5 layers of glass, then you're going to get this. You can get 5 different refractive events. And then, of course, if you have many more layers, then it's going to turn into a curve. And of course, with the Earth's atmosphere, it is actually, the layers are just a molecule high in effect, and so you're going to get a nice beautiful curve, and it will behave exactly in the same way as this does, which is a practical observation. And you're going to get exactly that same curve, the curving down towards the denser medium. I can't remember why I started this description now, but yes, everything curves down. So you've got a lateral refraction, but you can get super looming versions of that. So the only complexity of making observations, you can get observations that don't match the simple formulas that I used, that you saw me present earlier, for allowing for refraction. You are going to meet conditions, because of course things like mirages and things like that, inverted mirages, those are not in, the formulas I presented do not account for that. And so that's why you have to use the ray tracer. That's why Philip and I have been working on this ray tracer for the last 6 months. Although I must admit, we sorted out most of it at the very start. And that models, and that's why if you want to model everything perfectly and allow and account we can account in the ray tracer, we can actually account for inferior mirages, everything. We can account for all of Anthony's observations, but you can't do it with the simple formulas and things that you might come across. So there are complications that real life doesn't necessarily match the round Earth model, the spherical model, if you just use the simple Earth curve calculator thing. And so that means you just got to understand when those conditions are abnormal. And you do things like get very close to the ground where you're in the refraction layers, inversion layers and stuff like that, or very dense layers where there's a transition between cold air and warm air and things like this, where you're going to get sort of mirage type effects and looming, super looming. So that can't be modeled just with a simple formula. You then need to do the ray tracing, which is what we've done, and with that you can then model everything. So yes, in most simple cases, certainly like Isaac did here, where you're not involved near the ground or near refractive conditions, it's going to conform to the usual 7 over. I don't know if you've heard of this at Catz, this 7/6R compensation, which allows for the right, because so that graph that I showed you of the density changing with height, that uniform, that's pretty standard. Once you get above this sort of messing around near the bottom where the air's heating, all this sort of stuff, if the atmosphere is uniform, you then can apply the simple forms. That's why it works so well with this. My formulas work so well with that Isaac's picture here, is because you're well away from all the messing around with those turbulent refraction conditions, or that can be different. And on this particular graphic, because you're nice and high up and you're looking at something a long way away that's also high up, you can just apply the simple formulas to get good results.
Rumpus, I might point out that 7/6R figure, where that comes from, is that's over decades of observation that geodetic surveyors have made and measurements. It's kind of an average value for a starting point that you're typically going to find on the Earth. But if you really want to know what's going on in any one given particular situation, at a minimum, you need to know the temperature at the target and at the observation point and average them to figure out what your actual refraction is. But without having that information, 7/6R is a pretty good starting point.
Yeah, I've actually looked into the history of it, and actually there was, I can't remember there was a famous physicist who had a value of 0.1. 7/6, I think, gives you a K value of 0.17, and the value they used to use was 0.13. And so they have changed what you do, but this situation, that's of course, again, with geodetic surveyors, that's where you're quite close to the ground. I think when you're in this situation, when you're well above it, then it is more standard. So
your extreme refraction tends to occur within about the first 4 or 5 feet above the Earth, and if you get upwards of about a couple meters, 10 feet, 12 feet, something like that, 3 or 4 meters, you're getting above the extreme refraction area that's close to the Earth. So if you're making any of these sorts of measurements like I did, you really want to be about 3 meters, 10 feet above the Earth at least, to get out of that zone where you're going to have a lot of density gradients.
Yeah, and of course the thing is that what people like Anthony and other flat earthers do is they look on the horizon. So when you're looking at something like the Isle of Man or something across water, you're looking looking at a horizon. That point, you're actually looking through just a few meters high of air. So that's why you get these effects, because you are actually looking at that very thin there. Because of course you look down to the horizon. At the point of hitting the horizon, you are actually looking through air of that type. Whereas here, in this situation with Isaac, we're not. We're looking across a thing. We're not trying to look at something through a horizon.
Right. Yeah, you can see that you're considerably above the ground, and where the above the tree canopy, where there would be a lot of heat variations going, you're well above it, which is good in this.
Yeah, I mean, obviously, Isaac is actually standing on the ground, and he's close to, but he's actually
but his corridor, his optical corridor, way above. I mean, there's a valley down below, basically, so he's well above the refractive effects or the thermal gradients.
Exactly. Yeah, as you say, the optical corridor is free, is almost entirely free of, and doesn't go through a transition. I mean, if it's just around you, it's not such a problem. The light doesn't get a chance to curve. What you need is something, something in the midpoint between you and the thing you're looking at and staring at it. I don't know if I've got any examples of.
Yeah, we might point out that this 7/6R figure, what it does is, what you're doing is, rather than using the actual radius of the Earth for your calculations, you increase it by a factor of 7/6, which makes the Earth, the refraction makes the Earth look bigger than it actually is, because it's raising objects up in the distance and making the Earth look flatter than what it really is. So you use a slightly larger radius to do these calculations, so it flattens out the surface of the Earth.
Yeah, and indeed, as you've observed, haven't you, George, that if you get into these extreme superluminous conditions, sometimes it can actually appear to be the Earth is flat when you get.
Or concave even.
Indeed, yes, yeah, quite. So when you're looking close to the ground, you can get these strange. Now, here's another example. This is Soundly's some pictures Soundly took, and here. This demonstrates, for instance, I mean, you get idiotic. It's really weird. You get people like Riley who say that light doesn't travel in straight lines. Does travel in straight lines, and then the refraction does nothing or something. And then yesterday he was talking with Sly about he was trying to include the subject of refraction because he's now discovered this friend, this pal, this flat earther who's now talking about light refracting up. So suddenly he's interested in it again, interested in refraction. Well, previously for a year he's been saying light always travels in straight lines. Well, okay, then how do you account for this? This is a picture Soundly took in two different atmospheric conditions from the same position of the Marriott Hotel in New Orleans. So he's in the same conditions, different conditions, same place. And look, this hotel has jumped up by a factor of God knows what. So
sure.
So hold on. If light travels in straight lines, what is causing that? Is it on springs? No, I think we can have to assume the atmospheric conditions have changed, which means that light is not traveling in straight lines in one of these two conditions. And of course, with the mirage, is he claiming light's traveling in straight lines here? Well, in which case, we've got a very strange-looking object. Do we see this object here? Yes. Oh, is it that what the object looks like? No, because you can't rely on what you see unless you're a moron like Nathan. I mean, these idiots are just unbelievable imbeciles. So this is a wonderful demonstration of looming in action and how refractive conditions vary in the same on the same objects, and how important the refraction can be if you're looking at in the situations where you're looking across the horizon at something in the distance and the refractive conditions change. But if you're not, and this is again the Isle of Man observation stuff, and here, for instance, a simple one. This is how I'm having an argument with Sly at the moment about what inferior mirage is. These are all little inferior mirages because you can see here from the ripples in the road that these are curved areas. By the way, you still do get refraction on a flat Earth. Some people some people do deny this. A flat thing still has refraction. It's just much less. The rounded nature of these little dips here do induce inferior mirages. And on a circular Earth, because of the angle that the incidence occurs onto the refractive layers that I was showing in my atmosphere thing, it is more pronounced. Refraction is more pronounced on a spherical Earth, but it still occurs on a flat Earth. It seems that people don't quite understand that. So these, for instance, these images. So do we see? Say what you see. Say what you see. Okay, I see this strange mushroom-shaped thing. Is that what's there? No, because the light's bending. So I mean, idiotic arguments. Right. So I've done my bit. I don't know if everybody's happy to carry on talking or something, or is anything else to say on this?
Or do you want me to talk a little bit about the measurements I made? Or
yes, George. I mean, that would be, as I say, Riley's now got on to if you want to put your refraction or your measurements, that'd be fine. Just so yes, if you wanted to point out the flaw that Riley's now claiming that light bends up, yeah, you go ahead, George, and demonstrate that this was and this idiot in Brighton who's got a handheld thermometer who claimed that because he's then discovered that that temperature goes up, therefore things bend up, and which is now being appropriated by Riley. Yeah, if you want to invalidate all that, that'd be great.
What we'll need to do here is.
Do you want to share your screen?
A screen share. Yeah.
Okay. You put something on screen and I'll share it for you.
Okay, hang on here.
I'll present you.
Darn, there it is.
So while you're doing that, George, so Isaac, are you going to do some more observations on any of this thing? I don't know what more you can do. You've done a pretty good job.
Well, yeah. What do you think about those other pictures I took in the?
I haven't looked, I'm afraid. I've been panicking like crazy with this. I haven't had a chance to look at the rest.
Well, yeah, no, like I told Conspiracy Catz, it rains like crazy around this time, so I haven't had another clear day since I first sent it to him. But yeah, any type of observation we need, I'm literally minutes from
that's amazing.
And just getting anywhere.
167 kilometers. That was a fantastically clear day. That was to get that.
Yeah. Yeah. No.
Are you getting my screen yet?
Yep. Okay, I'll present you. Hold on, sorry.
Well, anyway, you're getting at is, guys, what Rumpus had said earlier is I built a, thermistor array. What I have is a pole that's about a little 1.5 meters long or so. And I mounted 5 thermistors on it, spaced 30 centimeters apart, so that I could hold it up in the air. I have a pole extender that I could put on there where I could get it up as high as of around 8 meters or so above the ice. What I have here is a very large freshwater lake, and I'm on a bay that's about 6 miles across. Canadian shore is 2 miles to the north of me and 6 miles to the east of me. And I set up targets out on the ice on poles at various heights. And I set up some equipment. I have an observation point where I have surveying auto level and a theodolite, where I can mount them up about 12 feet above the ice and shoot across the ice out 6 miles. And then what do with an auto level, set up a tangent that's going out from the observation point, and then go out on the ice and adjust the target heights so that they intercept the tangent line. So after going back and forth, looking through the auto level, then seeing where the target is, going back, adjust the target height. So I had a number of targets out on the ice, spaced a mile apart, every half mile or so, going out to 6 miles, and spent time adjusting the target heights so that they would be in line with the tangent back at the observation point. And then I had another set of targets that were set up on the same poles that were 73 inches above the water level. The way I establish the water level is I pop a hole in the ice. I'll show you here. Is this coming through now?
Yep, you're presenting.
Okay. I have this ice auger here to drill through the ice. The ice at this time of year is typically anywhere from 30 to 40 inches thick out on the lake. This here you're seeing, I'm viewing out on the Canadian shore. That far shore there was 6 miles out there, looking across the bay. And what I have, snowmobiles, and of course Con that joins me on the snowmobile when we go out. And on this particular test, what I have here is for a Bedford level style test is I had to drill a channel through the ice to get into a deeper spot. The ice where I had the auto level set up was almost frozen right to the lake bed, so I couldn't pop a hole to get the water to come up. So I had to chew this channel through the ice and get out a little further out, away from shore.
Oh, I see. You're trying to get the water to come in to the auto level. Are you from further away?
That's right. Yeah, the auto level would be mounted so that the center of the auto level would be at the center of that one hole. So what you'll see here is
one thing, George, you haven't mentioned why the water level is important to you.
Yeah, why the water level is important is given what the ice is all floating out on the ice. So, or the ice is floating out on the lake. So this is just like a big ice cube. If you pop a hole through the ice to the surface of the water level will come up in the hole and seek the proper level. The surface of the water in the hole will be at the height it needs to be, because the ice floating on the lake will not impact that. That if all the ice was gone or melted, the water level would be the same in that hole, whether or not there's ice there. That's just the property of the buoyancy of the ice, of Archimedes' principle, that the weight of the ice will displace an equal weight of the water. So whether, like if you put an ice cube in a glass and you marked the water level with the ice cube in it, and then you let the ice cube melt, that water level will not change. That's just the property of how the ice behaves when it floats on the water. So the important thing is because there can be variations on the surface of the ice in thickness and roughness, you can't necessarily guarantee that the ice level is going to be within going to be at the proper level or the proper height at any point, you know, on the surface of the ice throughout the whole bay. This way, by drilling a hole in the ice and letting the water come up, you know exactly where the proper water level is. So that's the whole idea here, is you by each of the targets, you pop a hole in the ice, let the water level come up. Now you have a reference point that the water level will be at each of the holes will be at the proper level to give you a good reference to measure to, rather than measuring to the surface of the ice. And the other advantage that you have in the wintertime here is in January and February, where I was doing this experiment last winter, is the air is so cold it precipitates all the moisture out of the air. The air is extremely dry, and you get these very good optical conditions. You don't have haze or moisture in the air that blocks your view, and you get these clear, very pristine days, and you can see out, 20 miles or so with very, very good resolution. So,
I mean, the great thing about your idea, George, which you thought of a year and a half ago, was that whereas you obviously you like to do something, a huge echo here, if you wanted to do this over land, of course, you wouldn't have a reference point. And of course, if you do it over water, then of course you'd have to build a little island or something. But of course, because you've used the ice, you've used your ice basically little islands across the water, and you've been able to use water to get the uniform level. You can reference the water level to know exactly how far each pole is above with regard to your auto level. So your great idea about using the ice and then being able to drill down to the water level to get the right reference point, you have all the advantages of being on land and all the advantages of water being uniformly having a uniform height above the center of the earth. So it's a great idea you had there.
This is the auto level here, mounted on the tripod that I shoot out, and here I'm taking the camera to show you the water in the channel. Is to bring the water in to the auto level. That's why I had to build that channel, is to get the surface of the water throughout that whole channel, of course, is going to be all at the proper height. So
you know exactly how high you are above the water level, and therefore you know when your poles are mounted how high they're above the water level, and you know those two things are the same thing.
Right. So there's water there. Okay, now let's go. Now, I'll show you the targets that I set up. This is a target at 0.7 miles away from the observation point. The height of the target is 5 inches. The targets are not all the same size. In order to take care of perspective so that all the targets will look basically the same height as I'm looking out over 6 miles, as you go out further, the targets get progressively larger. The first target at 0.7 miles, which is this one, like I said, is 5 inches across. By the time I get to 6 miles, the 6-mile target is 63.5 inches in height. It's a huge target.
I'd love to see a flat earther try and determine how big the target should be at different distances. I bet they couldn't do that simple calculation.
Okay, so this is the 0.7 mile target, and the way I have these targets set up is I have these two triangles, an upper and lower, so that when you're looking through the spotting scope of the auto level, you can gauge where you are towards the center of the target, because you want to sight the centers of the targets. What's happening here?
I thought you were going to get on to showing us your thermistor rack. That's the key thing that.
Oh, shoot. The photographs aren't, it's not changing.
Because obviously with
Yeah,
the
on the, I don't know.
because we want to invalidate this charge by the recent new charge that things refract upwards, and therefore the modeling we're doing on the spherical Earth doesn't match reality because we're not using the right refraction. So
here's the target at 1.36 miles. I have an upper target which is adjusted to be at the tangent to the Earth back at the observation point, and then the lower targets are for the Bedford level style experiment, where they are 73 inches above the surface of the water. These are the lower targets are all fixed at 73 inches above the surface of the water, whereas the upper targets are adjusted so that they're in line with a tangent line. This is at 1.36 miles. This is at 2 miles. I just have a lower target at 2 miles. Again, this is center of the target is 73 inches above the surface of the water. This is at 2.72 miles. I have an upper target and a lower target. Again, the lower target is 73 inches above the surface of the water, and the upper target is adjusted to be in line with the tangent. This is at 3.5 miles. I just have a lower target. You can see that the targets are getting considerably larger now. This is the 4-mile target. I made these orange so that they'd be easier to spot by the spotting scope. This is 4 miles out from the observation point. Again, the center of this one is 73 inches above the water. And then this one's been adjusted to be in line with the tangent. You can see that the heights are for the upper targets are getting considerably higher as we get out further away in order to be in line with the tangent.
And so the key thing here is that the water, you know what the water level, see George has dug a hole next to it so he can find the water level, and then he now knows how high the target is with respect to the water level, so he can guarantee exactly how high that is with respect to the water level, and then he knows how high the observer is with respect to the water level, and therefore you can do all the relevant calculations and observations.
Here I'm out at 6 miles. I'm mounting the target up in a tree. Jesse Klauslowski is here with me. Jesse and Soundley came out and visited me for 3 days last winter, and Jesse came out to the 6-mile target with me, and we were mounting the target. This is Jesse's equipment here for precisely locating coordinates, his Trimble. And again, I'm in the tree here adjusting the target, and here's Jesse with his equipment, and off to the right here I mounted a corner reflector for shooting a laser to it. Plus, here's the target. As you can see, it's considerably larger than the other targets. So this is a target mounted up in a tree, up on the island, on a hill on this island, out at 6 miles. The center of this target is actually close to 35 feet above the ice.
Yeah, I mean, we're getting slightly off track here, I think, George, aren't we? I mean, we should probably do a separate hangout on this.
Yeah.
Well, I was hoping you...
What did you want?
Well, I was hoping you'd be able to demonstrate from your practical observations that the guy who's the new attack line from Riley, that light refracts upwards based around the fact that temperature...
On the thermistor measurements, looking at the thermistor measurements is, again, I have this thermistor pole with these precision thermistors mounted on. The thermistors are guaranteed just off the shelf to have a repeatability between thermistors of 0.2 degrees centigrade, but I went ahead and calibrated my array so that I know that my thermistors, I have the Cal constants for them so that I can measure the temperature differences within 0.05 degrees centigrade. I calibrated them against laboratory thermometers.
Yeah, brilliant.
And this is much better than trying to use a bulb thermometer or anything, because you can electronically measure the resistance of the thermistors and then from the Cal constants get the exact temperature. And on the array, I had them mounted 30 centimeters apart. And like I said, I could mount them also on a pole to extend it up. And what I would do is I'd go out and I would measure the temperature in what I call the optical corridor. Is the thermistors would be held up by the targets, where the target centers would be at the center of the array, and then I'd record the temperature around the target. And I found that I learned how to recognize days in which I would have minimal refraction. And on those days where I went and adjusted the target heights and made my measurements, I found that the cooler air is always near the surface of the ice, and it gets a bit warmer as you get up off the surface of the ice. But within my optical corridor, over a 1 meter plus minus 1 meter from the target center, I was having less than 1 degree centigrade variation. So it was fairly stable.
Actually, George, another amazing thing, of course, you discovered and invalidates this idea of light traveling in straight lines and that we can't rely on what we see, is, of course, you were getting the relative positions of these poles were moving around hour to hour, weren't they? They were changing their respective positions due to refraction. So you therefore know that light doesn't travel in straight lines. You can't.
Now here's a view. Yeah, here's a view through the auto level looking at the lower targets. All these lower targets are 73 inches above the surface of the water. This is the one here at 0.7 miles. This one is at 1.36 miles. You can see that the center of the target, this one's a little bit lower. Then this one is out at 2 miles. This is at 2.72 miles. This one's at 3.5 miles. This one's at 4 miles. And as you can see, even though the targets are 73 inches above the water, that the further you go out, the lower that they appear, from a straight tangent drawn out from this target. And in fact, they don't line up with a straight line either. If you're to connect the centers of the targets, you're going to find it's more of an arc, which it would be on a spherical Earth.
So all those things should be in a line. All those lower targets should all be in a line on a flat Earth and aren't. And what's more, we know with varying refractive conditions, they all jiggle up and down with respect to one another. Both points, of course, invalidate the position of flat Earthers.
Yeah. Here, stop it
great,
there.
Great
you can
stuff there, George.
get it
really.
good.
Have we got a picture?
I have more updates going yet to post on this. This is just kind of advanced.
Okay. Have you got pictures of your thermistor rack? Have you got pictures of your thermistor rack, George, demonstrating how careful you are about your temperature measurement?
I don't know if I have it.
Okay, the point you've established, you've made these measurements using as you were talking about, your very accurate thermistors, and you could demonstrate that basically this idiot on Brighton Beach was waving around a handheld thermometer, God knows heating up or God knows what else, has absolutely no idea what he's talking about.
Yeah, well, you have to keep in mind, I went out every day for a period of about 60 days. I have a vast ream of data that I've taken, and the vast majority, I mean, you're talking well over 90% of the days that...
Whoa. Sorry, that's my end. I'll just mute that with 1 second.
The well over 90% of the days, you will find that the air is denser or cooler near the surface of the Earth than it is above the Earth. And the gradient varied, but you're always finding that the cooler air is near the surface of the Earth. But there would be conditions like around sunset where that can reverse rather quickly, because as the sun starts getting near the horizon, especially out here on the ice in the wintertime, is the upper air cools down very quickly as the sun rays go away, whereas near the surface of the Earth, the air is still a little bit warmer. And so you get the temperature inversion, and then you get some really weird effects occurring right around about an hour before sunset, and right at sunset, I could see extreme compression going on.
Yeah. And that is backed up by the paper that I'm going to be showing in my presentation, my other presentation, which exactly backs up what you said, George. I remember you telling me this about over a year ago, and then I found this paper which actually logs exactly the refractive conditions over the period of the evening. It shows as you go into an evening, you get this superlumin conditions, and of course those are the same conditions that Anthony Riley observed the Isle of Man at. And the variation is quite huge, as you say. It's interesting you observed it, and there's a paper that, you know, there's an academic paper that's approved, verified, and peer-reviewed that makes exactly the same thing. So, yes.
What I want to show you here is this was suggested to me by Jaron at Globebusters. He wanted me to do this, where I would take a theodolite, which this is, and line up the first two targets. This is the 0.7 mile target. This is the 1.36 mile target. And you can see that I've lined up the centers of, I've adjusted the
height of the targets
on
right.
theodolite so that these two target centers are in line. And then you look at the other targets, and again, you see that they fall below the center line. And
so all the targets, you didn't change the height of the targets, then you just changed the height of the target?
No, these are all 73 inches. And
right.
what I've done is I've taken the theodolite and mounted it on another tripod about
right.
4 feet behind the auto level. And of course, I had to adjust the level or the height of the theodolite to point slightly downward in order to get these two targets to line up on the crosshairs, because this target is going to appear a little bit higher than this target in actuality. So you have to kind of put the theodolite a little bit higher and aim a little bit downward to get these two lined up. But even when you do that, these targets, as you get out further away, still drop below the center line. Jaron thought that all the targets would line up this way. If I lined up the first two targets, then all the others would line up in line with it. But you can see that they do not. They drop away from the center line the further you go out. This orange one, again, is at 4 miles out. This target is 3.5 miles out. This is at 2.72 miles. This is at 2 miles. This is at 1.36 miles, and this is at 0.7 miles. So
right. We're going to have to do that. We're going to have to do a thorough hangout about this, George. I think yes, definitely. We've got lots of material here. Yeah, we need to prepare this and do a proper.
But anyway, it's just kind of a preview of what I'm working on.
That's really good. Yeah. Okay. Well, does Isaac?
No matter what you do, no matter how you set up your equipment, the targets do never line up. You can never get the targets to line up.
Yeah, I mean, you're one of the few people to actually know a practical experiment that really knocks the flat Earth into. We can say things, but you've actually done the actual experiment and observations that demonstrate it using a very. I thought the idea of using the water underneath the ice is just a fantastic way of doing it. Better than having islands on.
Well, the other thing too, of course, is again, here's the auto level. This is where this is the TopCon theodolite mounted about 4 feet behind the auto level, taking the photographs, the previous photographs. And then up here on the hill, this other tripod, this is where I move the equipment mounted on this tripod to be 12 feet above the ice.
As you can see, George takes this seriously. This is a lot of work George had to put in here. And he's got a digger as well there, moving ice.
Yeah, the center of this auto level is 73 inches above the water level. But this is the observation point. You can kind of see, we're looking out towards Canada out at 6 miles. But this is the home base of the observation.
Okay.
And this is the equipment that I was using.
Yeah, we're going to have to do a serious hangout about this, George. I mean, this is just really just rock solid, fantastic stuff. We should have to give it a premier proper hangout of its own.
And then I have 2 reference poles here this is 100 feet away. This is 400 feet away. And I have marks on these where these targets are 73 inches above the water, so that, and then you can see all the targets in the distance over in there. But this is all looking out on the bay. If I stop, whoops, let me, you can kind of see, let's see, get this back. Yeah. Whoops. See, way back here, that little spot there, that's the 6 mile target. This is Home Island, that's just 6 miles away. And then you can see the various targets here. And then I have a couple reference poles for calibrating the equipment and making sure you can just above the water level.
Rightio. Okay, George. I mean, we really are going to have to do this properly on this your thing, because just so much material there and so much to learn, and it's just so rigorous. Yeah, just fantastic. I don't think we've got anything else to say about the Isaac observation here, or anything subject want to bring up, or has been put on the chat, or anything, or Isaac or Catz?
Yeah. Hold on. George, did you say you're from Minnesota? Did somebody mention that?
Yes.
Oh,
yeah,
okay.
I'm on northern,
on
the Canadian border.
Okay, I grew up in Minnesota.
Pardon?
I grew up in Minnesota.
Oh, where?
Apple Valley. Apple Valley.
Oh, okay. Yeah, you're in Minneapolis area.
Yeah, cool. I know exactly what you're talking about.
Yeah, I'm up in I'm in International
the
Falls.
Northern Woods, or International Falls. Yeah, great high school hockey teams up there.
Right. Yep.
Yeah, no, one thing I just wanted to say before we go, because I mean, obviously with all these numbers and data and math stuff, they're done. But when Riley comes back and tries to state that it wasn't a trap, I'm stating right now, it absolutely was a trap, and he fell for it. Done. Yeah. That's all I gotta say. Okay.
Right. Yeah,
I hope he listens to this, because we could, it'd be interesting to show him. But it absolutely, I think Conspiracy Catz knew exactly how they would react, and he planned it, and it couldn't have went off any better.
So. Well, I mean, you could actually, I mean, you tried to get him to believe. You sort of imply it didn't make Catz made it sort of slightly difficult to for somebody who wasn't rigorous in their thinking. He made it easy for him to make a mistake, but of course he made a huge mistake anyway by not accounting for the observer height in his calculations of angular size.
Yeah.
So he managed to compound the error he made about what the height was with his own mathematical errors.
Yeah.
So we shouldn't be saying he proved anything with his maths, because he didn't prove it. He just got everything wrong, and that doesn't prove anything. So we've got to be careful about claims.
It's not as much fun to say that. It's not as much fun. You don't wind him up as much by saying that.
Yeah, Catz. You definitely value. There's definite value.
We talked about it. I actually did the original calculations from peak to peak before I did a second calculation with that side peak, because the side peak was easier to visualize. If it was just taller, then that made sense. The peak to peak, they were both shorter. But so I sent both of those to him, and I explained to him, that I didn't want him to get confused, and he just had this look in his eye and this grin, and he's like, "Don't worry about it. We got it. We're gonna." What'd you say? You said we're gonna give him a little rope to hang themselves.
Yeah.
And that's exactly why he did. It was meant to be slightly vague. It wasn't to be to deceive them or lie. We had all the numbers. I just did two different calculations, the original peak to peak and this second one, so yeah, that's how it all started, and it was absolutely all his idea, and it was one of the greatest things I've seen on the internet for a while.
Catz, I think it's really great the way Dell helps you out. I'm amazed he's prepared to give you that time. Just really
I think he's a good guy. He's a big fan. We get on really well.
I mean, but he put so much effort into it. That's just impressive.
What's what? Sorry.
He put so much effort into your videos. That's just...
Oh, he does. He really tries, doesn't he? And he changed his personality. He once commented on my video, and I did say, because I'll be honest, I don't like whoever it is. I don't like trolling him and stressing him out. And he did make a comment, and I've said to him, If it stresses him out and he finds it offensive, me using clips of him, then I'll stop. But he didn't want to admit that he didn't like it, so he actually gave me permission. I got the screenshot. He said, "No, use them as much as you like." So
that's very well. There's a typical kind-hearted Glober there. You know, you could be abusive, but you know, you think just consider everyone's feelings. It's very, very nice. Yeah, very good, Catz.
Brilliant. But no, I think that this mountain thing on top of the Miles Davis photographs, I think we're going to see like a flood. If we haven't already, because I'm obviously new to the game, so I've missed quite a bit. But I think we're going to see a flood of photographs that people are going to claim this is impossible on a flat Earth, and one after the other, it's just going to be relentless now.
Yeah, I mean, Sly kicked it off. It was about a year or so ago when he did this thing where he's in somewhere in Germany, and he was aligned a mountain with a building or something. I think a tower in the distance, and he said, "Yeah, no, these two things should be aligned." And then Mars, yeah, and I thought at the time, yeah, that's a good way of demonstrating it. And then obviously Mars picked that up, decided to try it out with his fortunate position where he's able to get to that height, and then of course he found himself at the same height of that. Was it some tower? Was it Trogmore monument or something? And so yes, yeah, indeed, anything like this where when you've got this great situation when you've got two things at very great distances from one another, and you know from the model, your model can say whether or not they will line up or not, and therefore you've got the photographic evidence whether they do or not, allowing for refraction, of course. But it's not so great in the situation, particularly if you're doing tall things like Isaac's done. You don't tend to get big refraction issues, which is a big help. But yeah, I think you're right. I think it's an easy way for people to demonstrate to test their models. And
all you need now for anybody, all you need is a bit of working trigonometry, you know, to understand, don't you? You know, the angular size of something. You know, is the angular size of one, should it be bigger than the other? You know, it boils down to something pretty much anybody can grasp, doesn't it?
Absolutely, yeah. I mean, the formula I presented was quite complicated about when you alpha the curvature of the Earth, but you can pump it into the mixed West calculator, then just do the simple subtraction of the visible from the hidden, and then just work out where your the horizontal, so you know what should be visible. And yeah, so my formula made it a bit more complicated than it was, but it's just working out the angular size. And of course, the thing that Anthony and Riley did wrong was he took the absolute size. He didn't allow for what was being missed off. He didn't allow for the observer height. So he was just comparing the full height of the, which he didn't allow for the hidden. So I mean, just.
Well, that's what I mean. Your math was, you know, it was. I didn't mean to suggest yours was complicated, because what you've done when you predicted it with the curve of the Earth, that's where it gets difficult. You know, like for me, you know, I'm not a mathematician on your level by any stretch, but I can just say, well, it doesn't fit a flat Earth, and then give you the difficult maths to prove that it's exactly what it should be on a globe.
And of course, when you've got someone like the ray tracer, then of course you can actually produce a lovely image of the two situations, which I thought was absolutely great there, where we could see this is what you would see on model. The model of the spherical Earth gives you this image, the model of the flat Earth gives you that image. And of course, one of them agrees with real life, and the other one doesn't. And then, of course, from that you can get results. So, but yes, but yeah, just simple people just lining things up that shouldn't line up, and you can do much simpler calculations. Yeah, perhaps I should do a website in which you can just pump in some values, and then it does all that calculation for you. Yeah, so then we did. I think you're right. I think we encourage people to go and do that, and then possibly, yeah, get a little calculator. I'm sure Walter Bisley I'm sure could do the same for people as well. He's yeah, because I keep on meaning to do it. I meant to do a Walter Bisley Earth curve calculator about 6 months ago, but didn't get around to it. And but now he's done exactly an ideal thing. So yeah, if you want to do proper Earth curve calculators, which does the images that in the Walter Bisley calculator, of course, does include perspective, and of course the MicWest one doesn't include perspective and doesn't have to allow for it because it's not creating an image. Because as I showed in my little diagram about things moving further away from a camera or closer together, side elevation, it's only when you want to create an image. It's an imaging operation, perspective. If you're not creating an image and mixed West calculator is not creating an image, you don't need to include perspective. You only then need to include perspective. You then want to include the results, like a mixed West thing says you've got so much hidden, and you then want to know what that looks like in an image. You then have to convert either the image into absolute values, or you need to convert the absolute values that the Earth curve calculator gives you, and then import those into the image. Now, you can do that in a oh god, I could go on about that. There's another way. The analysis I did on Rantis things, where you need to work out what I mentioned earlier, that the angular size, each pixel is an angular size, represents an angular position, and what you can then do is convert that into absolute meters. If you know the distance to something, so for instance, in the Yeah, before I sign off, just quickly share this thing again. Whoops. Which is an important concept. So, for instance, in this situation here with Isaac's picture of Mount St. Helens, what you would be able to do, quickly do this. As I was mentioning earlier, you would try and end up with a and then similarly, you would try and say this is each one of those would represent a particular degree, and then you could also whoops, I didn't mean to do that. And then you could form a little grid across here of angle positions, and so if you know you can use a technique whereby working out what the pixels per degree are. You do that by finding something in the picture you know the distance, the angle to, and the angles between it. You can then work out the angles, the degrees per pixel in your image, and then you can say, "Haha, right, I know the." I can then work out the number of pixels equals a number of degrees, and if you, for instance, then know the distance to something like this ridge here, which was 86,000 kilometers, if you know from image analysis what the degrees per pixel are, you then know the distance to the ridge. You can then say, aha, well, let's say this is 40 pixels wide, this ridge here, if you can see that. So if we say this is 40 or 50 pixels wide, and you've worked out from image analysis what the degrees per pixel are, you can work out the number of degrees it is, and then using that formula that I showed you about the angular size, you can invert it to get, you can convert from angular size into real size. You can actually work out, just from doing image analysis, the absolute size of this, for instance. So the way I tend to work is not to convert the results of the Earth curve calculator into angular sizes. What I tend to do is to convert angular sizes from the picture into absolute sizes. So, for instance, I could say if I knew, for instance, that I was looking at something of a particular height, I could say, in fact, I might just quickly show. Right. So, for instance, here is an observation. Here's something I haven't publicized yet. This is a thing I was doing analysis on Ranty's observations, and he did of a video of Nookie Nook from Nicky Nook of the Isle of Man, and I was able to work out, for instance, here the degrees per pixel by knowing the Benny Fott mountain and the North Pole. I could then work out the number of degrees this was. That meant I then could work out the degrees per pixel. So then I could then work out how much was visible of this mountain here. So, for instance, here I can then say, right. I know the degrees per pixel in my image. I can see this much of the mountain. And so then I can then convert that, because I've worked out what the degrees per pixel are, I can then work out how much of this mountain is visible. And so then I can then put that into the Earth curve calculator. So, for instance, here, here's the top of, I think it's Snaefell, yes. And we know that Snaefell is 620 meters high, which means that the base of Snaefell is actually here, underneath the water. And so you can then compare, you can say, well, okay, this is where the base is from knowledge of it sitting 620 meters. And because I've worked out the resolution of the photograph, I know where the base of the mountain is. And then you can say, aha, so how much of this is missing then? And then it gives you the hidden value. And then that is a value you've got in meters, because you've done the image analysis. This is why Nathan says, oh, but you haven't accounted for perspective. Where was the perspective calculation? Well, you don't actually need to do it. You do an inverse perspective calculation, because you can work out the absolute size from the image of the hidden value. You can then compare it to the absolute size of the hidden value from the Earth curve calculator. So you actually do need to do an inverse perspective operation. You don't need to do a perspective operation. So you use the absolute values from the Earth curve calculator, and you determine absolute values from the picture, and then you can compare the two. And of course, as it turns out, in this image of Nicky Nook, which Ranty claimed invalidated the spherical Earth because it wasn't compatible with it, if you then do the calculation, do the image analysis, you work out that the image is telling you the number of pixels hidden is 37 pixels, and the Earth curve calculator says, sorry, turn that into meters, it's 262 meters, and the Earth curve calculator says it should be 267. So of course it agrees perfectly with the Earth curve calculator. So that's how you can avoid, you don't have to use perspective, but you can use inverse perspective. Anyway, that's a bit of an aside, and that's probably more than enough than anybody wants to know. Right, okay, so unless Isaac or George or Katz have got anything else to say, I'm probably going to end it here. Unless there's something in the chat that I should be taking notice of. So I haven't been looking at the chat. I've been too busy thinking and looking and presenting.
No, the important thing to keep in mind is that in the vast majority of observations, you're always going to have the normal conditions where you're going to have denser, cooler air near the surface of the Earth and warming up as you get higher above the surface of the Earth. That's the normal condition.
So warming up. Sorry, you said warming up, going up. It gets colder, doesn't it?
I said warming up as you get up off the surface of the Earth. That's the normal condition that you're going to typically find. You're going to have less dense air above.
So did you say warming up? Sorry, I didn't hear warming up. Did you say
warming? Yes, getting warmer as
hold
you
on,
get up.
Hold on. You're saying it gets warmer as you get higher?
Generally, yes.
No. It definitely gets colder as you get higher, George.
If you go up, high. If you're going up hundreds of meters, but up off the surface of the Earth, you have cooler, denser air closer to the surface of the Earth when you're within, say, 50 feet generally of the surface of the Earth. You have denser air near the surface of the Earth, cooler, denser air.
Hey, Rumpus, can I say one thing?
Yeah.
I got to go, but
yeah.
It was a pleasure meeting you guys. That was an awesome presentation. I hope to hear from you guys again.
Okay, we'll do it again, Isaac. Yeah.
Yeah, and I can't wait when you get the website up with all the data and links and everything you did, the map. I can't wait to see it. It was just excellent.
Oh, I'm glad you.
Thank you so much for having me.
Well, thank you very much, Isaac. It was great. Thank you for taking that photograph. Absolutely brilliant, and a pleasure to analyze it.
Yeah, no, of course. All right, bye guys. Bye, George.
Bye, Isaac.
Bye, Kat. Talk to you later. Bye.
Later, Isaac.
Rightio. Okay. Well, I'll end it here unless Katz has got something you'd like to end off with, Katz, or something.
No, just that was. I think you smashed it. You smashed it out the ballpark there. I wouldn't expect them to put any effort into any kind of serious rebuttal, but anyone with half a brain who's seen that, they know, don't they?
Well, the rebuttal will amount to just words with no actual measurements or data to back it up. I mean, that's what they always do. They make up this bullshit stuff like angle of attack and other stuff.
Oh, God, Rayleigh's criteria.
Who came up with that? Was that Nathan's original brainchild?
Just made stuff up, no basis in anything, no science. They keep on asking us for citations, and they just make stuff up. And this Rayleigh's criteria, absolutely irrelevant to things disappearing from the bottom up. Air is diffraction. They don't understand what diffraction is. They don't understand it's completely irrelevant, and so is Rayleigh's criteria. I mean, it's just absolutely. Oh, by the way, I was impressed, Katz, with your showing of Franhauer diffraction patterns and things. That was excellent to see. You didn't show them for very long. In your video.
On the Baldy Cats when I did the Rayleigh criteria. Yeah,
that's good. Yeah, because that's quite
I'm beginning. Well, I'm sure where Nathan and Riley come in is particularly Nathan is adhere to the old model. If you can't dazzle them with brilliance, baffle them with bullshit.
Yeah, I mean yes. I mean, just assert stuff completely unfounded and just makes stuff up. It's just incredible. And this side elevation allergy, and I've been using side elevation, but you use side elevations to work out what the perspective. What they don't understand is that you have a perspective image, which is like the view from the ray tracer, and you can work out using a side elevation what that would be. They don't understand it's two separate things. You convert one into the other. Oh, God. Anyway, I just got to get onto another subject if I can, like this, and that would be another 2 hours.
Well, somebody should take a few minutes sometime and explain to Nathan how a atmosphere thinning out as you go up above surface of the Earth is
we
not
should
a
do that.
violation of the second law of
Yeah,
thermal.
George, we should do that. Yeah, or Catz want to join it. Yes, we should possibly do a week, every week end or something. We should do a quick summary of the idiocy that we've been subjected to, and quickly debunk it. But yes, you're absolutely right, George. We shouldn't let this vacuum business in space and the entropy lark and the what the other ones.
They don't seem to understand that you can reverse entropy on a local level by inputting energy into the system.
Yeah.
Exactly.
And of course, reference frames is another thing that we need. There's about 6 or 7 major outstanding things that we haven't really properly contradicted in a video or two, and we should really do that. It's just so stupid. There are 13 and 14-year-olds out there that I think would have Catz must deal with children that have a higher intellectual level and a greater level of understanding of science than these flat earthers.
Absolutely. Like my year 8s, like 12-year-old, they can talk about refraction, they can talk about refractive index, they can do the Snell's law calculation.
Wow.
The 12-year-old kids. And they can talk about why light would arc, etc.
That's impressive for 12-year-olds. You must be pushing them quite well there, Catz.
we do refract. I mean, I'll be honest. The school I'm at the minute has it's got a selective intake,
right?
So
a
lot of gifted and talented.
Yeah, that sounds quite good for a 12-year-old to get Snell's law to do calculus. I remember doing that. I think I was about 14 or possibly 30. Yeah.
Catz, the one thing I have found, though, and the benefit of a lot of this flat Earth nonsense is it has allowed me to introduce a little bit of humor into the classroom when talking about geometry and some concepts of physics. You can use it as a springboard to show, why a lot of this stuff is such nonsense.
I think humor. I think anything like that where you can introduce a bit of humor really switches people on, doesn't it, and gets them. They remember what they've been taught as well if you can put it in that context. Yeah. They walk away and they remember it. Yeah,
and I think you've got to compliment it again, Catz, where anybody introduces the Boltzmann distribution into a description of something. I think it's definitely got to get plus marks there. I think you did well there.
The funny thing about that, I mean, I just sort of threw that in because it happened to be what I was teaching in my A-level class at the time, but. Anthony's reply to that was, well, it's just a statistical probability. But but his argument about entropy, when you look at entropy, yes, we know what entropy is, and we know that entropy, like we can predict it, but even entropy itself is a statistical probability.
Yeah, I'm just interested. You're saying you teach that to A level. I must admit that's quite good for A level. I would have thought that's degree level stuff, the Boltzmann distribution. If you do anything with it.
What we do is we'll use it for, to be honest, pretty much the example I use in the video. So we have to understand that it works out a proportion of something, and we use it. It's bigger in chemistry, and I don't teach A-level chemistry for rates of reaction, but for us, we go as far as saying, well, what percentage of nitrogen should be at X altitude in the air? It's this temperature. You've got to work out the potential. Well, you know how it works, but you work out the potential energy. You look at the temperature, blah blah blah, and you try and figure out what proportion of nitrogen atoms can reach a certain height.
That's quite sophisticated, actually. Yeah, I mean that's the sort of stuff that I would expect.
Yeah, that's not trivial stuff. Yeah.
Yeah, I mean I couldn't do that off the top of my head now. I'd have to go away and think about that and look at the equation and. Because you'd have to work out from the bottom you work out from presumably the energy. Oh, you do it from potential energy. Saying right, yeah. I see. Right, okay, yeah, that makes it a bit easier, I suppose. I was thinking the density, but yeah, I suppose if you did it from just potential energy, that would make it. Yeah, okay, that's a bit of an easier approach.
It's pretty much plug and at A level. It's plug and play. You get the equation.
Indeed. You do derive the odd things in A level. Yeah, I was about to ask you if you derived it. I thought no, there's no way they're going to be doing that.
No, we don't derive that one. No.
I was thinking about trying to introduce that to Nathan's group, but I figured it'd be beyond their capability of understanding that. Yeah, I mean, you can have.
They can't do reference frames.
You can have some oxygen and nitrogen escaping the Earth, but percentage-wise, it's so minute compared to the vastness of the atmosphere, it's insignificant. Whereas with helium and hydrogen, almost all of it escapes.
It's well, I don't think Nathan's group could spell Boltzmann, so might struggle with anything more complex.
Oh, I'm kind of curious. I kind of picked up a little bit on this thing that Riley's doing about going back to school or something and demanding Catz that you have like a fiduciary responsibility to introduce an alternative like flat Earth into the curriculum or some darn thing like that.
And I know what he's talking about. And this. Oh, have you got 2 minutes, Rumpus? I don't want to go on. I know you're looking to close, or.
No, I'm happy to. I just don't want to bore. I mean, I don't know whether I'm boring people in the chat or you're boring you or something. Well, you go ahead.
Well, just to put that whole kind of thing into context, when I first met Anthony, it's because one of the kids I taught asked me if the Earth was flat, and I thought, well, I'll just contact some guy on the internet and some random guy. We'll have a discussion. It wasn't even a debate, It's like, let's just have a random discussion, and it was he publicised it as a debate afterwards, even though I promised him I wasn't going to correct him on anything, but. There is a law that says that as a teacher we shouldn't belittle kids about the beliefs, and that's just common sense. We shouldn't belittle them, and we should accept their viewpoint.
I noticed that's the way you treated him, the Catz. I know. I was thought you're being really kind to him in all the before you realised what he was like. Cat, anyway, sorry to interrupt you, Catz.
No, you're right. I mean, that's what it was. At that point, I didn't know who Nathan was. I didn't know who Del was. I didn't know who anybody was. I didn't have any interest in flat Earth. It was purely an exercise for, let's have this discussion, and then the kids that I teach might then start to ask questions themselves and just get a bit more excited about science because they've seen the teacher on the internet and he's debated this guy. But I think Anthony's taken from that, and he's found this law. I can't remember what law it is that he's looked at, and I think he's got in his head now that we've got a duty to teach the kids about flat Earth. But that isn't what I was doing. I was just trying to get them when I went in on a Monday.
Is it the Hippocratic Oath you're talking about, something equivalent of thereof?
Yeah, whatever.
Well,
what the doctors take. The doctors take Hippocratic Oath.
Sounded more like it sounded to me when I saw that law poster or something. If I read it right, it just seemed more like it was geared towards political leanings or political.
Absolutely, yeah.
Rather than anything having to do with hard science.
Yeah,
that political views should be tolerated.
Okay, I'm going to end with, unless you've got anything more to say, Catz.
But the thing is, if he's doing this, if he's demanding that, then he should probably go to the medical schools and demand that they teach bloodletting. And, next time he feels ill, he probably should cover his body with leeches.
And the 1 + 1 = 3. Why are we disputing that? I mean, God. What just being... Philip wants to join in. Yes, hold on. Just let me give me a.
But I mean, why stop at flat Earth? Why not, promote bloodletting for curing a cold?
Exactly.
I was going to end on a little question about how many reference frames are there in this diagram, but Philip is about to join us. But while he's there, this is a little question I posed to Nathan in one of my things, and there are so many objects in here. There's a rotating Earth. This is supposed to be rotating Earth, and these are a number of objects on here, all moving in different directions and with an atmosphere. I asked how many reference frames were there in this, and that's a question I think I'm going to leave people with. But unless Philip joins in,
well, the thing is, I think we had a recent discussion that we can have an infinite. Okay,
George. Honestly,
I know the answer. Is it infinite?
Yes. Oh, yes. Oh,
sorry about that.
Got it.
Well done, Catz. I think you just demonstrated your well on the ball there.
Oh, that's Philip.
Philip Weinberg. Yes, this is Philip. Yes.
You've called him Philip. Yeah, I put him in a video a few weeks ago, and I can't remember what it was, but he'd made some brilliant comments on a channel I was reading, and it was excellent. Is he on with us?
Yeah, he's now here. Yep, Philip is here.
Hey, Philip.
Hey, can you hear me?
Yep.
Yes.
Great. Yeah, I just got into my office actually. So I just wanted to comment. Well, okay, I won't disrupt the conversation as it's going right now, but I wanted to talk a little bit about refraction since we've already kind of discussed it a bit.
Go ahead, Phil. Yeah, well, I think, you'll feel free.
Well, I don't know if I was interrupting anything.
No, we were just aimlessly chatting and no.
Well, okay, so basically, I mean, I think you guys already covered this, but there's multiple ways you can actually show that refraction does not work the way that Anthony Riley has been claiming that it works. And so, Rumpus, you went through the layers of refraction using Snell's law, and that was actually a very intuitive way of actually figuring out how refraction works. But you can actually use the full equation to approximate how much refraction will happen and which direction it will go. And basically, I'm not going to do it now because it's a bit technical, but at some point we should do a hangout and discuss this.
Definitely. Yeah, you know, any technical stuff you want to do a hangout on, I'm game. I've got to announce to everybody. I've got Philip did this ray trace, and he and I fixed most of it about 6 months ago, and I've just been awful at getting this bloody website finished. And poor Philip there's been chomping at the bit trying to show off his lovely ray tracer, which he and I have been sort of discussing, been through all sorts of things with problems with globe Earth. Information about the terrain and things, and so many issues about adiabatic expansion rates, and thousands of issues which we sort of resolved. And then I've been lax at getting this website. We will do this other presentation, and Philip will get a chance to show off his wonderful ray tracer. So apologies to Philip. Well done. He's been very patient with me, so thanks, Philip.
Yeah, well, it seems like you've got a lot of stuff going on, so that's
I'm always calm. My life is almost back. I've things like deer hitting my car and God knows numerous other things in my life that have made me really and having a cold for 6 weeks. So yeah, I'm back on the case now. Anyway, so Carol, Philip, what were you saying?
Well, basically, you can show that the curvature of the light ray is proportional to the density gradient. So how which direction the density gradient is going. And actually, the Rumpus has a very nice plot showing this, which we'll keep under wraps for now, but we'll discuss it during our next hangout. But basically, you can show that because the density of the air is decreasing, you can show a direct mathematical correlation to the curvature of the light ray, which basically says that the curvature of the light ray will be such that it will be curving down based on the gradient in density. And this matches exactly what you'd expect, because when you have things like inferior mirages, this is when the rays get bent up, because the gradient in the density actually gets inverted. And so this is a reasonable explanation as to how refraction actually works, and it goes along with how Snell's law works. So just anywhere you really do it, it just doesn't work for what Anthony has been showing and what this other guy has been showing.
I just want to say the stuff that Philip had got this ray tracer, as far as I can see, no one else, even in academic literature that I've found, has attempted to do the stuff with inferior mirages and things that we've been able to do, even in academic literature. So this is, hopefully this presentation will have some, reasonably novel scientific stuff. Perhaps someone else has done it somewhere, perhaps in some film studio or something, but not that I've been able to find in the academic literature to the level of being able to model inferior mirages and any of the other sort of mirage.
Well, I think the difference is that I've seen in my research, I think we've come across lots of literature where they do kind of
on pictures,
simple models. Yeah, they're trying to render refraction and render mirages on images. So basically, if you think about the rays heading out, they're hitting a two-dimensional surface in the distance.
Yeah.
Right. But there's actually something. Yeah.
Well, Philip, wouldn't maybe a simplified way of stating this is say that light seeks or moves into denser air?
Yeah. Yeah. That's like the two-word soundbite. Light bends towards the denser medium. So in this case, the denser medium is near the surface of the Earth. So light is bent down.
In the usual case, unless you've got inferior mirages and things. But of course, in this situation we're describing like here, there is not.
Yeah, from my measurements, what I was saying, Rumpus, is that well over 90% of the time, you tend to find cooler, denser air near the surface of the Earth than above the Earth.
So you mean the surface?
That's your ice, of course, does that. But normally, the normal gradient is that it gets cooler as it gets higher. In the usual...
I think, George, your observations are interesting because they happen over ice, and I think generally the ice kind of makes the air cooler at the bottom. But there's another aspect that you're missing here, because it's not just the temperature, but it's also the elevation that matters. Because in this model, you have to take into account the weight of the air on top of each other.
That was the other
So
point.
it's actually a counter. It doesn't always behave intuitively in terms of how much expansion the gas actually has.
Yeah.
You really have to work out because I remember me and the Rumpus spent a lot of time like trying to figure out our intuition on this stuff.
Yeah.
We'd just be scratching our heads like this model doesn't make any sense. And then, why is the air cooler above, but somehow the density gets higher and stuff, like very counterintuitive things like this. And it's because you have like the effects of the weight of the air above you.
Yeah, but over land, things are more unpredictable because, say, in the morning, as the sun comes up, the land is cooler than the air, and then as the land warms up, as the sun gets higher during the day, the land will actually be warmer, or the air above the ground will be warmer than, say, the air 10 or 15 feet higher. So you'll have these transition periods of transition throughout the day where things change, and then you get near sunset and the ground is warm, very warm, and the air is starting to cool off,
Yep. And that's when you start to get looming, right?
Yeah. Oh yeah, you have very strange things going right near sunset.
Yeah, and
the gradients are so extreme at that point.
Right, but I think the key point is that with these newest observations, this is all stuff which happens near the surface of the Earth, and in the case of Miles Davis observation and this what's this guy's name? Conspiracy Catz? Ike, I guess.
Isaac, yeah.
Isaac, yes. His observation, they're all taken over rough topography.
And high up,
and
very highly elevated, and he's looking at something, and he's not looking through near the horizon, anything, no air near the surface of the Earth.
Right. So any arguments that this is being caused by refraction is just patently false. There's no way, unless you get an extremely large and unstable gradient in temperature over a vast distance like that, you will never ever be able to see anything like this. And like the Rumpus, what you were saying earlier, the gradients you can calculate what those gradients are, and they're so steep that in the case of the Mount St. Helen one, it doesn't go to zero at the elevation of Mount St. Helen. It goes to zero at about 2 kilometers, which is well below the height of Mount St. Helen. So it's just refraction cannot account for these observations. Like it's just a physical impossibility based on the laws of thermodynamics.
The advantage that I've had doing these things out on the ice is the air. If I say have a day where the air might be there'd be a slight breeze, 5-10 degrees coming across the ice from the west, that's blowing the air 2 miles across the ice before it gets to me, and then is blowing it down the optical corridor. I'm on the west end of the corridor viewing east, and it's pushing the air across the ice going down that corridor. I find that the air is very stable both down the corridor and also vertically. So my conditions tend to be considerably more predictable than what you have over land. I'm always finding that I have a layer of denser air above the ice and a little bit warmer as you rise up above the ice, but the gradient isn't very much. I mean, we're looking, the extreme gradients that I've seen is maybe 4 degrees Celsius over a 3-meter elevation from the surface of the ice on up to 3 or 4 meters. But in my optical corridor about my targets, where say I'm 60 centimeters above and below the center of the targets, I'm seeing less than a 1 degree Celsius temperature change in that corridor. Right. So my air is fairly stable in the wintertime.
Anyway, I'm going to have to, I think I'll try and bring this to an end before we're going to 3 hours. So I'm going to act the school teacher here, and I'm going to give some scores out on how all we've done. I think it's 10 out of 10 for George and his experimentation, 10 out of 10 for Phillip on the ray tracer, and 10 out of 10 for Catz. So getting that infinite number of reference frames right. Excellent. And good night.